Okay, so most of what we go over today to do with naming is going to be a review from Science 9, right? You learned how to name simple binary ionic and molecular compounds, hopefully, in Science 9. All right, so we'll kind of review that, but then we got to expand on it because you guys didn't learn about like polyatomic ions in grade 9. Okay, so we'll have to look at those in terms of how they work with ionic compounds. We'll also have to look at how some of the metals on the periodic table actually have more than one possible charge, and that can change the way that we name the compounds they produce. Okay, and so we have to learn how some of these new rules. They're not really hard, they're just new. They'll be in addition to what you already know. Okay, so how can I tell an ionic compound from a molecular compound? Or let me put it a different way. What's in an ionic compound? Okay, a metal and a non-metal. All right, so how do I tell metals from non-metals? Well, on my periodic table, there's the staircase. Okay, on my periodic table it's red. On yours it's just a darker black line. Okay, that separates the metals on the left from the non-metals on the right. Okay, minus hydrogen, which actually behaves as both. Okay, hydrogen can behave as a non-metal. If it loses an electron, it can behave as a metal. Sorry, I said that wrong. It can behave as a metal if it loses an electron. It can behave as a non-metal if it gains one. Okay, in a chemical reaction, because it only has one electron, it's able to do that. Yes, we call those the metalloids. Okay, so things like germanium and antimony and polonium and bismuth, they behave oddly. We rarely name anything to do with those because of that. Yeah, they're very exceptional types of things. All right, so good to know. We know the difference between ionic. So a molecular compound then has, okay, just what in it? Just nonmetals. All right, so molecular compound is made only of things to the right of the staircase. Okay, so the goal of today, be able to write the formulae, that's plural for formula, okay, and proper names for chemical compounds. All right, so ions and ionic compounds. Okay, so an ionic compound occurs when we have a metal and a nonmetal joining together in a chemical reaction. All right, what typically happens in an ionic compound is this. Metals will give up electrons and nonmetals will accept them. Okay? The reason for that is that according to Bohr, who was, again, we don't really accept his model anymore, but he was right about how electrons move from one atom to another. Okay? According to Bohr, there are energy levels in which electrons reside. He represented them with the rings. Okay? In his mind, and in what we've seen in experiments, atoms are always seeking to have their outer ring or outer shell of electrons full. That's why chemical reactions occur. Chemical reactions allow atoms to fill their outer shell and achieve a more stable state. Okay? A reaction is always going to produce a more stable state of matter. Right? So when they fill these outer shells with electrons, they can do that in one of two ways. By taking electrons from someone to fill their shell, or by giving away electrons and thus losing their outer shell and having the one beneath already full. Right? So if we're looking at sodium, okay, as an example, right? So sodium's atomic number is 11, okay, which means it has 11 protons, it has 11 electrons. Okay? So sodium, okay, if this is just sodium's nucleus, I'm just going to write it like this. Okay, its first orbital where electrons can be found, okay, whether it's a ring or whether it's a weird shape, can only hold 2 electrons. Okay, the next shell can hold 8. Okay, so we'll just put them in there. Okay, according to Bohr and de Broglie, actually, electrons will pair up weirdly within a single orbital. So we're just going to draw it as rings because it's easier to envision that way. Okay, now that's only how many electrons? 10. So sodium's outer shell, which is capable of holding 8 electrons, only has 1 in it. So for sodium, what's easier? Losing 1 electron and having a full outer shell, or finding 7? losing one, okay? And metals are like that. Metals have their outer shells less than half full. So it's much easier for them to find somebody who wants their electrons, like Craigslist for electrons, okay? I put my electrons on Craigslist or Kijiji or wherever, and somebody will take them, okay? Because somebody always will, all right? For chlorine, if we're looking at like sodium chloride, okay, chlorine has the opposite situation, which is why sodium and chlorine are meant for each other, okay? Chlorine has its first shell full, its second shell full, and its third shell almost full. It's got 7 in it, yeah. Okay, because chlorine's atomic number 17, right? Okay, so it's got 7 of 8 spots in its outer shell full. So these two get along famously because they each have what the other needs. Okay, sodium needs to get rid of an electron, chlorine desperately needs one. Okay, so they form an ionic bond. Okay, ionic bonds are not very strong because, and don't take this from a sociological perspective, once they react with each other, they both kind of got what they wanted. And there's really no reason to stay together. Again, don't take that in a sociological perspective. There's really no reason for them to stay together after they got what they wanted. So, okay, ionic bonds can break very, very easily, which is why typically ionic compounds dissolve easily in water. They're highly soluble. Okay, their solutions conduct electricity. These are all things we'll learn later on. Okay, but ionic compounds tend to behave that way. Okay, molecular compounds do not behave that way because they don't trade electrons. They have to share them. Okay, so their outer shells get filled by sharing electrons with another nonmetal. So they have to stay together or they'll lose everything. Okay, so molecular compounds are typically bonded incredibly strong, okay, whereas ionic bonds are incredibly weak because they're not built on a good foundation of sharing and mutual, I don't know, it really breaks down after that, but yeah, you get the idea, right? Everybody okay with that? Okay. Okay, so, and that's where this one here, you guys know Bond, right? Bond likes his martinis shaken, not stirred. Well, ionic bonds are taken, not shared. Electrons are taken, not shared. That's terrible. But you know what? You can't find a lot of really funny chemistry memes. So there you go. Okay. So when we're naming, okay, so we're writing the actual name out for an ionic compound, we always write the metal first and the non-metal second. You guys don't have to worry about these terms yet. Okay, they'll be more important in Chem 20, but okay, the positively charged ion is the cation and the negatively charged ion is the anion, but you don't need to know that. Okay, so we have a metal and a non-metal. We always name the metal first and the non-metal second. Okay, we do not change the name of the metal, but we do add an "-ide" ending or an "-ide" suffix to the non-metal. Okay, when we make the chemical name. Okay, so examples would be magnesium oxide. That would be MgO. Okay, or sodium fluoride. That would be NaF. Okay, or aluminum sulfide, and that would be a little trickier, but it'll be, I think, yeah. All right, something like that. I'll tell you how we get those numbers later. You guys remember the drop and swap? So you know how I got those numbers then. Okay, good. Now, things to remember. See all those names I wrote? What don't any of those names have? They don't have any prefixes, okay? Because we don't use prefixes in ionic compounds. When aluminum reacts and joins with sulfur, there's only one way for them to go together because their charges have to balance. That's why we drop and swap. So we don't need to put prefixes on there, okay? Because that's the only arrangement. Molecular compounds are different. We do have to use prefixes because they're sharing electrons. They can get together in any number of different combinations. So we use prefixes for those, but we don't use prefixes for ionic compounds. Okay, another thing that none of these names have that names usually have. Capital letters. This is a horrible habit for people to break. But chemical names are not real names. They're a designation. Thus, they are not capitalized, ever, unless you are starting a sentence with one. and then you would capitalize it. But other than that, they are never capitalized. And that's hard for people to handle. A lot of times people forget because we just want to capitalize things because it's a name and we should capitalize it, but it's not. Okay, so we should not capitalize it. All right, so names are never capitalized. Okay, when using formulas, we have to balance the charges of each ion. So a true compound should have a net charge of 0. All right, so if you're looking at your periodic table, if everyone can take theirs out. Okay, you will see that the charges for each atom are listed kind of in the top right-hand corner, right below the atomic mass. All right, so for hydrogen, you can see that it can be +1 or -1. All right, if we're looking at something like nitrogen, it's -3. Oxygen's -2. All right, and you'll notice that a bunch of the metals through the middle, okay, have more than one charge listed beside them. Okay, they like manganese can be a 2 or a 4. Iron can be a 3 or a 2. We'll talk about the naming ramifications for that in a little bit. Okay, but that's where you'll find the charges. So if we look at aluminum chloride, okay, we would have dropped and swapped 3+ with -1 in order to get that formula. Okay, everyone follow me on the drop and swap? Everyone remembers that? Okay, so if there's one aluminum and it's +3, and there's 3 chlorines and each of them is -1, does this thing come out to 0? It does, right? Because there's 3 chlorines, each that's -1 for a total of 3 negatives, and 1 aluminum that is a +3 charge. So it balances out, comes out to 0. Ionic compounds always have a net charge of 0. Okay. All right. Let's have you guys try just, where's my screen shade? There it is. Let's have you try just the first 4 for right now. Actually, I think you have them all in your notes package, but just for right now, okay, the first 4. And then we'll go over them together and see how we do. Okay, so our first one here, okay, we've got sodium with chlorine. So when we write that out as a chemical name, all right, that's going to be sodium because we don't change the name of the metal and we write it first, chloride. All right, so we drop the ene and we replace it with ide. Everybody all right with that one? Okay. All right, for number 2, K stands for potassium, F stands for fluorine, so this will be potassium fluoride. And I never spell it the same way twice. I think actually the U comes first, but whatever. Okay, for number 3, I have hydrogen with iodine. Now, here's the weird thing about hydrogen. Remember, it can be a metal or a non-metal because it can gain an electron or it can lose an electron. It's the only element that acts that way. How do I know if it's behaving as a metal? Okay, depending on what it's bonded with, yes, and also where it is in the compound. If it's where it is right now, what do we always write first? Metals. So if hydrogen comes first in a compound, then it's acting as a metal. If it's anywhere else, it's a non-metal. Water is the exception to every rule you've ever learned. Yeah, I know it's weird, right? Because yeah, you're right. Water is a molecular compound. Okay, they have a polar covalent bond, in fact. Okay, but water, as you'll find as we go through the chemistry unit, anytime there's a rule, water is the exception to it. It's weird, but it's true. Okay, it's also why we never write water as like hydrogen oxide or dihydrogen oxide or dihydrogen monoxide or like it could be named a whole bunch of different. It's water. Just call it that. Okay, yeah, it's easy. It's the only one we use the common name for. All right, so this stuff then is going to be an ionic compound because, as we said, hydrogen is listed first, okay? An example of a compound where hydrogen's not listed first could be something like, sorry, not CH3, CH4, ammonia, okay? Not ammonia, blech. Methane, that stuff, you know, fart gas, the smelly stuff, that's it, okay? So ammonia, you can see that hydrogen is listed second, and that as a result, it's behaving as a non-metal, okay? There are exceptions, but they're very rare. All right, so in this case, we have hydrogen iodide. Okay, what about number 4? Ca stands for calcium, Br stands for. Does the 2 make any difference to the name? It does not, okay, because it's an ionic compound. So this is just calcium bromide. All right, seems like you guys have got the hang of this. Finish them off. Give you a few minutes, and we'll go over the rest. So we'll quickly go over these here, guys. All right, so for number 5, Al is aluminum, At is astatine, so this is aluminum acetatide. Okay, and yes, I'm still going to write it aluminum, even though the International Union of Physics and Applied Chemistry has officially changed it to aluminium. I will never say it that way because it sounds silly. Okay, I don't drink out of an aluminium can, and I don't drive an all aluminium truck. Okay, it's just dumb. I don't say it that way. I'm not going to say it that way. Just not. So even though on the newest periodic tables, I don't think on the one you have. Yes, on. Yep, you have it as aluminium. Okay, it's spelled aluminium on yours. If you spell it that way, I'll still mark it right. I'm not going to go that far. I'm not going to say it that way because I'm too old to change. Okay. All right, number 6. Okay, we have cesium with sulfur. Does the 2 make any difference? Nope. So we have cesium sulfide. You can spell that with an F or with a PH. It makes no difference to me. Both are acceptable, okay, because sulfur can be spelled both ways. All right, number 7, we've got sodium with oxygen. So this is going to be sodium oxide. All right, and then for number 8, we've got barium with selenium. Selenium's a tricky one to get the "ide" in the right place. There's actually 2 different ways to do it. You can have it as, yeah, selenide or selenamide. Either one is fine. Yeah, so it can be selenide, okay, or it can be selenamide. Okay, yeah, either one is fine, but both, yeah, there's 2 ways to do it. Most people write it selenide because it's shorter, but selenamide is also acceptable. Okay, and then for number 9, we have radium and tellurium. Okay, so that'll be telluride. All right, and for number 10, lithium fluoride. Okay, and number 11, okay, rubidium sulfide. Okay, number 12, Sr is strontium iodide. Okay, and this calcium oxide, right? Okay, and then for number 14, magnesium selenide or selenamide. I never say it's selenamide either, but it is technically correct. Okay, I assume probably most people got all of those right. Now I want you to look through them and mark all the ones that have a capital letter wrong. See how much of a habit you're in. Okay. You really got to be mindful, right? Everyone just gets going. I'm getting them all right. Oh, wait, they all have capital letters. Yeah, watch out for that because eventually it's going to cost you. Okay, so make sure that you are breaking the capital letter habit on chemical names. Okay, it's like an email address. They just don't have capitals in them. Okay. All right. Next thing we need to look at are what we call the multivalent metals. Okay, we call them multivalent because they can lose more than one number of electrons. Okay, sometimes it can be 2, sometimes it's 3. Okay, but it varies on the form of this particular metal. All right, iron is one of the multivalent metals. It can lose 2 electrons or it can lose 3 electrons. Okay, now in the end, whatever it's bonding with, it bonds with. But here's the problem. If I have 2 people in this class with the same name, can that be troublesome? Yes. But thankfully, it's not too often I have two people with the same first and last name. It's happened. Okay, Chase, what was his last name? I don't remember. It was a number of years ago. But I had two Chase, there was the same last name. They were both same first name too. They weren't related. Okay, there was Chase something. And his first name was Chase, remember. They were both. But anyway, I had actually two people with the same first and last names. Okay, it was really, really weird. That can create a problem, right? Because they're not the same person. It was really a problem when I was entering grades. I'm sure at some point along the way I put Chase number one's work in for Chase number two. Okay, we actually had to do that. Like when they wrote their names, it was like Chase whatever number one. Never thought of that. They probably are like me though and didn't like their middle name. Some people don't like their middle name, don't like to be called by their middle name, so I'm not going to say because I don't like it. Okay, so in a case like this, okay, this can be a problem because this is iron oxide, yes? Well, if it's the other iron, so is that. They're not the same thing. Okay, here's where this becomes really problematic. Let's say somebody's writing a paper, okay, and they're talking about the health benefits of eating rust. But not that there are any, don't do that, okay? But you don't want to chew on a nail or something. But anyway, okay, let's say that that's what they were doing. So they've got this whole thing, and they're going this iron oxide this, iron oxide that, and they're talking all through this thing about the health benefits of how you can boost your hemoglobin by eating rust. You can't, don't do it. But let's say that they were doing that, and I'm reading this paper and going, gee, that stuff sounds pretty good. I should probably put that in my diet. But they're talking about this, and I use this, which is not healthy. It's poisonous. I don't know if it is or not, but let's just say, okay? Is that a problem? Yep. It's kind of a problem, okay? It's like me putting in marks for Chase 1 for Chase number 2, okay? It's a problem. So we have to indicate in the name of a chemical compound that has a multivalent metal in it, which charge on iron was there, okay? So we just use a little Roman numeral to tell people which iron we were using. So if I have this iron oxide, it's going to be iron 2 oxide because the charge on this iron is +2. How do I know that? Right, because oxygen is a -2 charge, and we don't write the numbers if they cancel each other out. Okay? So if I had to drop and swap, okay, and I was like iron +2 and oxygen -2, we wouldn't write 2 and 2, we just cancel them, and it's FeO. Everybody all right with that? So I know that iron had to be +2 because all compounds have to have a net charge of 0. Okay, so if I'm looking at this iron oxide, okay, this isn't going to be iron Roman numeral 2 oxide. This is going to be iron Roman numeral 3. Iron can only have 2 possible charges, 2 and 3. All right. Now, there's 2 ways I can go about this, and a lot of people just go, well, I'll just reverse the drop and swap. That'll work about 2/3 of the time. Okay, but it won't work all the time. Like if I'm looking at this compound here and I just reverse the drop and swap, I'm going to say it's iron 1 because there's a 1 here. Right? I got rid of the 2's. Okay? In this case, here's what I want to do. All right? I'm going to say that every oxygen has a charge of -2 because that's true. Everyone with me so far? I have 3 oxygen atoms. Each one has a -2 charge. How many negative charges do I have? Okay. So I've got 6 negative charges in total. All right? I only have 2 irons, and I have to get to +6 for this compound to balance out. So the charge on each iron is 3. That's how I do it. Okay. Obviously, it's a little more obvious with this compound, but some compounds you actually have to do this process every time. Okay, on some compounds because they're a little trickier. Okay, so this is iron 3+. So this stuff would be named iron Roman numeral 3 oxide. Okay, and those Roman numerals are a little bit subscript when you write them. Okay, everybody all right with that? Right, so we kind of write the charges and we figure out what the charges will be. All right, so let's try let's try a couple of examples here. So we already did this one. Okay, so we already did this one. So let's try this one. All right. So this is going to be, what's CO stand for? Cobalt. Okay, so I'm going to write cobalt. And this is sulfur. So it's going to be cobalt something sulfide. Right? I need to figure out which cobalt it is. If I look at my periodic table, the possibilities for cobalt are 2 and 3, right? Okay. So sulfur only has one possible charge. So we always look to the nonmetal. There are no nonmetals with more than one charge. Okay, so it's -2. Well, I haven't done it yet. I'm figuring out which one it is, right? I'm going to figure out which cobalt this is by going, all right, the sulfur is -2. If this compound's going to come out to 0, this has to be the cobalt with the 2+ charge. So this is cobalt 2 sulfide. It's not hard. You have to do a little extra thinking. Okay. All right. I'm going to have you guys try the next 4 here, see how you do, and then we'll go over them. Okay, so on number 3, I have Mn, which stands for manganese. Okay, and it's with chlorine, so this is going to be manganese with some Roman numeral, chloride. All right, so I have to figure out which Roman numeral manganese has on it. Well, it's pretty obvious from this thing here. Chlorine's -1, so manganese has to be +4, right? There's 4 chlorines. That's a total of 4 negative charges. There's only 1 manganese in this compound, so it has to have a +4 charge. So this is manganese IV chloride. Okay, in case you don't know your Roman numerals. I don't think you'll need anything higher than 9. In fact, realistically, you probably won't need anything higher than 5. Okay. He was clearly dropped on his head at some point. Okay. All right. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Those are our Roman numerals. If you don't know them, you can probably write them down. Okay. But you realistically will never, for this anyway, need more than 5. Okay. All right, let's have a look at, sorry, I should have put that in brackets as well. Okay, let's look at number 4 here. So Cu stands for copper, okay? And S stands for sulfur. All right, sulfur is always a -2 charge. So in this case, copper has a +2 charge. So this is copper 2, and then I have to change that because copper 2 sulfide. Pardon me? Usually, yes. I mean, I'm not a stickler on that. If you don't, I'll know. Yeah, because some people actually write them like this, right? They write them as lowercase. They shouldn't be, but they do. I'm fine with that. Yes, you should put the brackets around just so that we don't get confused with anything. Yeah. All right. How many people have done 5 and 6? Okay. So I'll give you another minute or 2, and then we'll go over 5 and 6. Okay, so number 5, SN stands for tin. So this is going to be tin something telluride. All right, what Roman numeral am I putting in there? What's the charge on tellurium? -2. Okay, so tellurium is a -2. How many telluriums are there? 2. This is why I said don't just reverse the drop and swap. It's only going to be right about 2/3 of the time. Here's one of those other times. Okay. Okay. So if there's 2 times -2 is -4. There's only one tin here. This tin has to be +4, right? In order to balance off all the negatives and get a net charge of 0. So it's tin 4 telluride. Okay. All right. Then we have mercury with astatine. So this is going to be mercury something astatide. Okay, and the charge on astatine is -1, right? So that means the charge on this mercury has to be +2. So this is mercury 2 astatides. All right, seems like you're getting it. Try the others. Okay, there's 4 more there. Okay, so how do we know when we're supposed to use a Roman numeral? Do I use it on all ionic compounds? Right, only when there's more than one possible charge. So when you're writing out the names for ionic compounds, you always need to go back and check. I mean, I know you guys have probably memorized most of the names, right? You recognize, oh, that formula or that symbol means this, okay? But always go back to the periodic table to check, make sure if it's got more than one charge or just one, okay? So that you remember to use. More often than not, people forget the Roman numerals. Very rarely do people over apply that rule, okay? But more often than not, they forget to put them in. So always make sure to check. Does this metal have more than one possible charge? If it does, then I've got to put in the Roman numeral. Okay, everybody with me there? All right. So let's have a look at these here. So for number 7, okay, PO is polonium. Oh, what did I just put there? Oh, a capital. I can't remember the last time I did that. Polonium. Okay, and with iodine, so it'll be polonium something iodide. This one's pretty easy. It's going to be polonium 4, right? Because every iodine is a -1. Okay, so this is polonium IV. Okay, iodide. All right, number 8, SB. It's a weird symbol. Okay, antimony. Okay, so antimony is with sulfur, so it's going to be antimony something sulfide. Okay, sulfur is always a -2. So how many negative charges do I have? I have 6. Okay, so what does the charge on antimony have to be to get me to +6? 3. I'm not adding, I'm multiplying. Okay, every antimony is a +3. There are 2 antimonies. 2 times 3 is 6. It would work if you reverse the drop and swap, but remember, it's only going to work 2/3 of the time, right? Okay, so this is going to be antimony 3 sulfide. All right, then we've got nickel with nitrogen. Okay, so it's going to be nickel something nitride. Okay, nitrogen's always a -3, so this nickel has to be a +2. Okay, so this is nickel 2 nitride, and then we have ruthenium with oxygen. Oh, they must have updated that. Okay. Yeah, because on mine it's 2 or 3. Yeah. Oh, see, this is what happens when you use a new periodic table. Okay. All right. So for you guys, then, yeah, that's not going to work because yours says it's only a 3. Okay. All right. So if it's only a 3, then let's drop and swap this. This compound should look like Ru2O3. Okay. Okay. Questions on that? All right. What if I have this compound? It starts with a metal, so it's ionic, but it's got 3 things in it. Okay, so this is something you wouldn't have done in Science 9. This is what we call a polyatomic ion. Poly meaning many, atoms meaning or atomic meaning atoms, many atoms. So it's an ion that is a charged particle made of more than one atom. If you look at the top of your periodic table, there is a table of common polyatomic ions there. Okay, you will find, as the title would imply, many common polyatomic ions. And you will find OHs in there. Okay, OH is called hydroxide. Don't ask me why, that's what it's called. Okay, so OH is hydroxide. I name this compound like I would any other ionic compound. I name the positively charged ion first and the negatively charged ion last. So this stuff is going to be sodium hydroxide. Okay, people get like really thrown when they see these things, but the naming rules are still the same. Okay, you're going to name the metal first and the non-metal or whatever else second. There's one change. Whatever these end with is what you write them as. Okay, so if they don't end in "ide," don't change them to "ide." They might end in "ate" or "ite," okay, or something like that. That's the way they need to be written. Okay, here's the reason. Otherwise, I might end up with, so up here we had nickel nitride. Nitride is nitrogen. This is nitrate. Okay, this is nickel nitrite. Oops, sorry. Okay, they have to end in different endings, otherwise I'll be writing the formula or the name for the wrong thing. Okay, so if it ends in "ate," essentially don't change the ending of anything in the table of polyatomic ions. All right, we'll talk more about that tomorrow.